Today we're going to look at limits. And we're really going to look at two objectives here, utilizing what's called limit notation and determining the limit of a function from a graph or from a table, and eventually from equations as well. Okay? But a limit is a very important concept in calculus. In fact, everything builds off of limits. And what do we call derivatives and integrals? They both involve limits when we define them. So it's very important that we understand what a limit is. We write it like this. Okay? It looks like this. Okay? What we say when we look at that, we say the limit of f of x as x approaches a is L. Now, that's how this is read. The limit the limit of f of x as x approaches a is L. Okay. The limit looks at what happens when x is really close to a. Not, very important, not when x equals a. We're not interested in that. We're interested in what happens as x gets closer and closer to a. So we look at this graph and we say this is our graph of f of x. We can look at the limit as x approaches -4 of f of x. And we can see on the graph, we go over to the graph and we see as x gets close to -4, here's -4, as x gets close to -4, the y value gets very close to 2. So the limit as x approaches -4 is 2. The limit as x approaches 3 of the same function, well, here's 3. And so 3, when x gets close to 3, it looks like y is getting close to, oh, I'd say maybe about 1.3 or 1.25, 1 1/4, somewhere in there. Those are both limits. Okay. Sometimes we have to deal with what are called one-sided limits. Because sometimes what the graph does on one side, it doesn't do the same thing on both sides. All of these, it was doing the same thing on both sides. Now, some of our graphs are a little bit more complicated, and we have to deal with one-sided limits like a left-handed limit. Okay. Which is written like this. The limit as x approaches a from the negative side. That negative indicates it's a left-handed limit of f of x is L. And of course we say that as the limit of f of x as x approaches a from the left is L. So very similar to what we had, we just had to add the from the left. And you've heard me say several times, I'll say the limit as x approaches a. The order of that, you can say the limit of f of x first, or the limit as x approaches a first. As long as you get it all in there, it really doesn't matter which way you do that. Okay, a right-handed limit. It's a very similar idea, but limit as x approaches a, this time from the positive side. Okay, of f of x is L. And the way we say that would be very similar to this, except it would approach from the right instead of from the left. Okay, let's make that clear what we mean approaching from the left and from the right. So if I'm on a number line, this is A. On a number line, the positive numbers go off in this direction, and the negative numbers go off in that direction. That's why we use negative for left and positive for right. Now, if we are approaching A, we can approach A from this side. This would be approaching from the left. And this would be approaching from the right. Okay. Notice these numbers are all going to be bigger than A, but they're going to keep getting smaller and get really close to A, but not quite get there. So if I had a number like 5 here, I could have 6 out here, 5.5. All these numbers as they go are getting closer and closer to 5. From this side, I might have 4, 4.5, 4.9. All those numbers are getting closer and closer to 5. Remember, with a limit, we care what's happening as things get close to the number, but don't equal the number. Now, here's a key rule. Key rule says this: the limit as x approaches a of f of x equals L. Notice that I don't have left or right here. This is the limit. Okay? In order for this limit to exist, the left and the right limits both have to be the same. So we say if and only if the limit of f of x as x approaches from the left equals L, and the limit of f of x as x approaches from the right equals L. The left and the right limits have to match in order for this limit to exist. Conversely, if this limit exists, then the left and right limits are the same. So let's look at this graph and look at some different limits that we might check out. Okay? All right, so let's look at the limit as the lim as x approaches -3 from the left of g of x, which is what we are calling this function is going to be our g of x. Now, -3 is here. So if I'm going to approach from the left, I'm going to approach from this side. And we can see that the curve, as we approach -3 from this side, the curve is approaching 1. So from the left, this is approaching 1. The limit, now if we do the other side, from the right, approaching -3 from the right, well, if I'm from the right, that's over here, and the curve, if I trace the curve from the right toward -3, that is approaching 0. So there's a jump in this graph here. There's a jump in the graph because these limits are not the same. So what this tells us then is that the limit as x approaches 3 of g of x does not, D&E, does not exist. Does not exist because these two limits do exist. From the left and from the right, they exist. But because they are not the same, this limit does not exist. Okay? Whereas if we have another example on here, where we have the limit as x approaches 2 from the left, well, we can see it's clearly from the left, it's clearly approaching 1. And then from the right, it is also approaching 1. So then we can write it all in one statement. So the limit as x approaches 2 is 1. Right? And this time, instead of, you see there's no value, there's an empty hole there. There's a hole in the graph. There's a jump here and a hole here. There are discontinuities. It's not continuous there. But this one is a hole because the limit is approaching the same thing from both sides. All right. Now, limits from a table, really it's from an equation that we make a table in our calculator. So let's say we want to take the limit as x approaches 1 of x squared minus 3 over x minus 1. One very important rule of limits. The first thing we should always try is to plug in the number and see what happens. If we can plug in the number and see what happens, that's what we should do first. The problem is, if I plug 1 in here, up here I'd get 1 squared minus 3, and that would give me negative 2. That's okay. Down here I would get 1 minus 1, and that's 0. So that I cannot do. Okay? I cannot have negative 2. I can't divide by 0. So I'm going to go to my calculator and allow my calculator to do the work. I'm going to put the function into y1 and then use the table. Okay? All right, so let's see what that looks like. We come here with our calculator. We hit y1, and I'm going to clear that one out. And in y1, I'm going to put this function, the x squared minus 3 over x minus 1. So we do alpha y equals, to get to the fraction, x squared minus 3 over x minus 1. And we're not going to graph it, we're going to go to the table. First thing we have to do is set up the table. Table set. So we go second window. And table start, we always whatever this number is that we're interested in, whatever x is approaching, that's the number we want in our table start. So I do 1. And my delta table, that's just how many, what am I going to go up by? Am I going to count by 1s? Am I going to count by 5s, by 10s? Let's count by 1s first and see what happens. We'll change that value, and we'll come back and change that value, and then we'll pick one that's very appropriate almost all the time. Okay, so second, now I go second, and then the table function right up here. So second in the graph, here it is, and you can see it says error at 1. That's because we got that division by 0. All right, so let's look. We can't really see a pattern here. I'm looking for a pattern. What's happening is, as these numbers get closer to 1, it's really hard to see a pattern, especially because 0 is actually quite a ways away from 1 when you're trying to get really, really close. 0 is quite a ways away. So let's go back to our table set, and let's change this to 0.01. And then let's look at our table. Now, let's get back to, we got to get back to 1 here. We should have changed that back to 1. Let's do that. Our table start back to 1 where we're interested in, and then go to the table. All right, so now we can start to see these numbers are getting really close to 1. 0.95, 0.96, 0.97, 0.98, 0.99, pretty close to 1. And these numbers just keep getting bigger and bigger. They get bigger and bigger. This is, 41, 51, 68, 101, 201. No real discernible pattern there, except that the numbers keep getting bigger and bigger. Okay. On this side, the numbers keep getting more and more negative. Negative 31. Okay. It does not look like anything is approaching, like it's approaching the same thing. Let's try one more thing with our delta table. And here's the delta table. 0.001 is a delta table I use most often. And I want to change my table start back to 1. I use 0.001. It usually gives me a very good idea of what's going on no matter what. So second table, there's my error. And again, these numbers just keep getting bigger. Okay, these numbers just keep getting more and more negative, bigger in the negative sense. Okay, it doesn't look like we're getting closer and closer to anything at all, and we certainly aren't. We actually, in this case, the limit, there is no limit. The numbers just keep getting bigger and bigger. If the numbers are going to just keep getting bigger and bigger, or bigger and bigger in the negative sense, then that is not a limit. That is, it does not exist. We'd say that limit does not exist. Okay? Well, let's try another one of those. The limit, as x approaches negative 2, of x squared minus 4 over x plus 2. All right. So first thing we should try plugging it in. We always should try plugging it in, see what it does. For negative 2 squared minus 4, well, that is 0. Because negative 2 squared is 4, 4 minus 4 is 0. Negative 2 plus 2 is also 0. So we have 0 over 0. It doesn't work because we're, again, dividing by 0. That doesn't work. Okay, so we've got to go here again. Y equals, let's alter this. So x squared minus 4 over x plus 2. Change our function. Did I do it to plus? I did not. Plus 2. Okay, so we changed our function to what we want. Go to our table set. Now we're interested in what happens when x is approaching negative 2. Make that our table start. I'm going to do my delta 0.001 from the beginning, because that's the one we like. So hit second table, and let's put it in the middle. And now, look at that. Look at that pattern here. We can see as these numbers get closer and closer to negative 2, this is negative 4.004, negative 4.003. These numbers seem to be getting closer and closer to negative 4. And then when we look on the other side, from the positive, these numbers, this is approaching from the left because these numbers are all smaller than negative 2. So we're looking from the left. Looks like our left-handed limit is negative 4. It's getting closer and closer to negative 4. From this side, it also looks from the right. These numbers are all bigger than negative 2, so that this is from the right. These numbers are also getting closer and closer to negative 4. We can see our left-handed limits, our right-handed limits, and our limit in general, all right there in that table. So we would say that this limit equals negative 4. Okay? Generally speaking, it's not always going to be true. It doesn't hold true 100% of the time. But if we have something like this where we plug it in and we get negative 2 over 0 or 7 over 0 or some number divided by 0, some number other than 0 on the top, that usually ends up in a does not exist. Okay? Whereas down here where we got 0 over 0, a lot of times that means the limit does exist. When these are both 0 on top and bottom, a lot of times the limit does exist. Down here, when they're not both, when the bottom is 0 but the top is not, that's when the limit does not exist almost all the time.